Hello everyone, we move on to Module 4 for Foundation Engineering. So the topic is all about lateral earth pressure. Okay, before we start with our discussion for lateral earth pressure, let us try to identify the learning outcomes for this module. So the first one is explain the differences between passive, active, and at rest lateral earth pressure. Compute Rankine active lateral and passive lateral earth pressure coefficient for a given type soil. Third, solve the equivalent lateral earth force, active or passive, acting on the wall, including the possibility for a multiple layer soil layers, water behind the wall, and a surcharge on top of the wall. So we'll talk about lateral earth pressure. That is the pressure that soil exerts in the horizontal direction. So it is important because why lateral earth pressure is important? It is important because it affects the consolidation, behavior, and strength of the soil, and because it is considered in the design in the geotechnical structure. What are those geotechnical structures that we are considering wherein the lateral earth pressure is very important? Those structures, the geotechnical structures such as basement, retaining walls, tunnels, deep foundation, and brackets. So basically those are the geotechnical structures that we analyze and we design, and we need to know the concept of the lateral earth pressure. So basically, vertical or near vertical slope of soil are supported, of course, by the retaining wall, cantilever, sheet pile wall, sheet pile bulkheads, brackets, and other similar structures. So what we have mentioned are those are examples of geotechnical structures. So as mentioned a while ago, lateral earth pressure is needed because in the proper design of those structures requires an estimation of lateral earth pressure, which is a function of several factors. Number one, the type and amount of wall movement. Second, the shear strength parameters of the soil. Third, the unit weight of the soil. Fourth, the drainage condition in the backfill. So we have an illustration for the presence of the lateral earth pressure, how it moves on a certain structure. Specifically for this illustration, this is a retaining wall. So we have different types or nature of lateral earth pressure. So we have three nature of lateral earth pressure. The first one, the wall may be restrained from moving. The lateral earth pressure in the wall at any depth is called at rest earth pressure. So the first illustration in figure 12.1a, this is an illustration for the first nature of lateral earth pressure, which is at rest lateral earth pressure. So meaning to say the retaining wall is restrained from movement, so there is no movement on the retaining wall. The second one is the wall may tilt away from the soil that is retained. With sufficient wall tilt, a triangular soil wedge behind the wall will fail. The lateral pressure for this condition is referred to as active earth pressure. So we have here an illustration for the second nature of lateral earth pressure, which is the active lateral earth pressure. So for this active lateral earth pressure, we have here an illustration for the retaining wall that has moved. There is translation along x direction. So that translation or the movement, it moved at a certain distance, which call that as delta H. So the movement of the retaining wall is away from the soil. So this is our soil. So this is the retaining wall. So as it moves away from the soil, this is what we call as active lateral earth pressure. The third one is the wall may be pushed into the soil that is retained. With sufficient wall movement, a soil wedge will fail. The lateral pressure in this condition is referred to as passive earth pressure. So we have here the third nature of lateral earth pressure. So we have the retaining wall. This is the soil. The retaining wall will move. So when the movement of the retaining wall is towards the soil, that is what we call passive lateral earth pressure. So there is translation along x direction. For the active lateral earth pressure, we designate as positive. The translation is at positive delta H. For the passive lateral earth pressure, the translation is negative delta H. So those are the nature of lateral earth pressure for this particular retaining wall. So this is a figure showing us the nature of variation of lateral earth pressure at a certain depth. So we have the different variation of the lateral earth pressure at a specific depth identified. So this figure shows the nature of variation of the lateral earth pressure at a certain depth of the wall with a magnitude of wall movement. So basically for this, we have different nature, two different types of soil that was illustrated, and we have illustrated the variation of the lateral earth pressure at a certain depth. So the first lateral earth pressure is the lateral earth pressure at rest. So for the lateral earth pressure at rest, you consider this vertical wall of height h as shown in this figure. So retaining soil having a unit weight of gamma, a uniformly distributed load Q per unit area is also applied at the ground surface. The shear strength of the soil is, so the shear strength is given by shear strength is equal to C prime cohesion plus normal stress multiplied to tangent angle of friction. So this is an illustration for the lateral earth pressure at rest. So for this illustration, you have at the depth h, you have the different parameters. You have your surcharge identified that is being applied on this particular illustration. So how are we going to identify the lateral earth pressure for a retaining wall that is at rest? So to identify, actually, you're going to review your soil mechanics on the computation for the vertical stress. So for the vertical stress, we try to you're going to compute for the vertical stress at different depths identified. Then after you compute for the vertical stress, you can compute, after you have computed this vertical stress, you can compute now for the horizontal pressure, which is now our lateral earth pressure. Once you have computed the lateral earth pressure, you can draw your pressure diagram. So this pressure diagram will be used to compute for the total force acting on the retaining wall. So that is one way to compute for the total force by having the resultant of the forces using the area of this pressure diagram. So basically, we are given with the parameters, cohesion, effective angle of friction, and the effective normal stress based on this given figure. So basically for this, as mentioned, you're going to compute for the vertical stress at depth z for the given illustration for a given retaining wall. So if you're going to compute for, since this illustration, we don't have the presence of water, so there is no presence of water, so we have here h, since the total height of the retaining wall, of course, which pertains to the soil that is being restrained by the retaining wall. So if we're going to compute for the vertical stress at depth z, so that would be vertical stress is equal to Q plus gamma times Z. So if you try to recall from your soil mechanics, basically, to compute for the vertical stress, that is unit weight times the height, or which is denoted by Z. So that is the formula for the vertical stress. However, if there is a surcharge being applied, so the vertical stress now would be vertical stress equal to gamma times Z, the unit weight times the height, plus the surcharge, which is Q. And you have this because this illustration, there is a presence of surcharge. So if there is no presence of surcharge, the vertical stress, this vertical stress is equal to your Z multiplied to our unit weight of the soil. So that is for the vertical stress. Once you have computed for the vertical stress, you can compute now for the lateral pressure at depth Z. So to compute for the lateral pressure at depth Z, you're going to multiply your vertical stress times the coefficient of at rest earth pressure, K sub O, or K naught. So this is now the lateral earth pressure, or that is what we call as our horizontal force. So if there is no presence of water, basically our horizontal force would be K naught, the coefficient of at rest lateral earth pressure, times the vertical stress that you have computed. And if there is a presence of water, so there would be plus pore water pressure. But if there is no pore water pressure, this is only the formula K naught times the vertical stress. So your K naught, which is our coefficient of at rest lateral earth pressure, can be computed whether if that is normally consolidated soil, according to Yaki's formula, that is K naught is approximately equal to 1 minus sine phi prime. Of course, you know what normally consolidated soil. But once we talk about normally consolidated soil, as we have discussed in soil mechanics, when the present vertical stress, when the present effective vertical stress is higher compared to the past vertical effective stress, that is normally consolidated soil. So this is the formula that you're going to use to compute for K sub naught, or coefficient of at rest earth pressure. However, if that is over consolidated soil, that can be expressed according to Main and Kolhawi. K naught would be equivalent to this equation, 1 minus sine phi prime times OCR raised to sine phi prime. So of course, we know that OCR is over consolidation ratio, and over consolidated soil meaning to say that the present effective vertical stress is lesser or lower compared to the past effective vertical stress. So this is the formula for over consolidated soil. So once you have computed now, as mentioned, for the horizontal force, you can draw your pressure diagram. So basically, the pressure diagram, how to draw the pressure diagram.